Now start the recording. Hopefully not too long, not too late. So this is one way to use relay in the discrete control system. Is a start and stop. So when we push start button, it will automatically latch. This contact will close, and it will latch on and energize the coil. So when the button is removed or released, this parallel latching, this parallel branch closed circuit will keep energize the coil. So the motor will remain start until we push the stop button. Stop button will shut off this coil, the energy, shut off the current to the coil, release the mechanical contact, and turn off the motor. So that's the one of the most common way to using a relay is building a latch. LATCH. This is called a latch. A latch has a memory. So a latch has a memory. That means once you push start button, it will remember the start button has been pushed, and it will keep remember that until you push the stop button to stop it. So this is the end of, and this is called a ladder diagram. So this is a relay ladder diagram because it looks like a ladder. You have two lines, one is hot, one is neutral, hot and neutral. And then you have circuits between hot and neutral. And this is the relay. And this is a normally open contact. This will be normally closed contact. So when you push start button, this red light will turn on. Why? Because the latch is on, and this will close, and that turn. This green will turn off. When you push stop, the green will turn on. Because when you push stop, latch will disengage, and that will close because it's normally closed. When this disengage, this CR1 will close, normally close will close. So the green will turn on. So this will be a start and stop button with two indicator lights, which give you a visual, show you the status, the state of this latch. So in order to draw a ladder diagram, we need a lot of components. First component will be relays. So those are the relays. These represent the normally open contact, normally closed contact, and that's the relay. And there's alternatively, the relays can be timed relay. I have one of those timed relay here. Let me grab. I just can't find it now. So a relay can be timed relay. That means it will have a delay. For example, if you have a 2 seconds delay, it will be a timer relay. Timer relay will have delays. That is actually very common in the sequential control. Why? Because sequential control is a sequence of events happening one after the other. So in a sequential event, we need a lot of timer relays. So for example, we start after 5 seconds, seconds in start, after another 5 seconds, start another event, another 30 seconds, we start the third event. So it's all controlled by timers. So timer relay is a very important component for this sequential, not sequential, discrete control. Actually, discrete control also called sequential control. So sequential control need timers. And the second component are the motors. So these are how we represent motors in a ladder diagram. solenoid, light, indicator light, the push buttons, the limit switches. This is a normally open limit switch, normally closed limit switch. And then we have pressure limit switches. We have temperature limit switches. We have level limit. So that will combine, we can build a very sophisticated sequential control system, or the author call it discrete time control system. So let's design one with an example. So this example is a very good example. Let's read what we're going to design. We will design an elevator. So that's before the computers. We have elevators. Today's elevators are now controlled by computers. In the old days, those elevators are controlled by relays. So we are designing one of those. So it will have an up button, down button, start button, and a stop button. Has two limit switches. So that's what and the two motors. So this elevator has a motor one for up, lifting up. Second motor for moving platform down. Why we need two motors? Because the assumption is those motors can only rotate one direction. If we have a motor can rotate forward and backward, then we only need one motor. If the motor can only rotate one direction, then we need two motors. Anyway, in this design, we have two motors. We have two limit switches. One is called up limit, right here, up limit. That's the triggered limiting switches. So you're actually mounting a little rod on this driving belt. And when the platform is up, and this will be the up position limit switch. The second limit switch is right here. It will be the down position limit switch. So you want to turn the motor off when the limit switches are triggered. So the elevator will stop. In this case, it's only 2-story, right? 2 stories. And then you have a start button, stop button, up button, and down button. So now we will design this control system to accomplish this sequence of events. So when start button is pushed, the platform is driven down. When stop button is pushed, everything stops. When up button pushed, the platform, if it is not in down mode motion, that is very important. When the platform is moving down, you do not want to change it to moving up. That will potentially be dangerous. Number 4, if the down button is pushed, if it's not in upward motion, then we drive it to down position. So that is the sequence of events. And now as a design engineer, we need to translate this into a ladder diagram, right? So based on the design requirement that is provided by your customer, we will get a ladder diagram. So this one-page ladder diagram is our design, one page. So first, let's look at what happens when we push start button. So this is the start button. This is a starting latch. So we push start button, the start latch will latch, and that's it. The start button latch will disengage when LS2 is triggered. What is LS2? LS2 is the down position limit switch. So the start button will start the motor. That is the down motor. This is the down motor. So the down motor will be started when we push the start button, CR1. So that's what the start button will do. So start button will start until it reaches the down position. That's the start button. Let's look at the stop button. This is a stop button. The stop button will energize CR2. What CR2 will do, it will disengage CR3. That's what CR2 will do. So the stop button do not have memory. Instead, it will kill CR3. That's the memory. So CR3 is the memory. Remember, everything is running until we push the stop button. When we push the stop button, it will kill this memory because CR2 will open. When we push the stop button, this is normally closed. Whenever we push it, this is re-energized. When it's energized, it disengage. It will open that. When you open that, CR3 will open. When CR3 will open, look at CR3. CR3 is here, CR3 is here. When CR3 is de-energized, it will open both motors. That will be the up motor, and that will be down motor. So this run, each letter horizontally are called runs. They have number 1, number 2, number 3, number 4, number 5, run 5, and run 6, run 5 and run 7. Run 5 is up motor, run 7 is down motor. So when we push the stop button, this will open and both motor will stop. Whenever it's moving up or moving down, it will stop. So that's the stop button. Now we go to the down button. No, this is actually the down motor. Now we look at the down button. Yeah, this is the down button. The down button will engage CR1 latch, CR5 latch. What is CR5 latch? CR5 latch will start the down motor. Yeah, right here. So whenever we push the down button, this latch will engage. CR5 latch engage. When CR5 latch engage, CR5 latch engage, the motor, the down motor will run. What about the up button? This is the up button. That's another memory. Whenever we see this setup, that's a memory. That's a latch. So we push the up button, CR4 latch will engage. When CR4 latch will engage, it will disconnect down motor. So those two motors will never run at the same time. Why? Because when CR4 is engaged, it will disconnect the down motor. And CR4 engaged, the up motor will be turned on. How about the down button? The down button will energize CR5. It will disengage the up motor. So these two, CR4 and CR5, is never turned on at the same time. CR4, CR5, CR4, CR5. CR4 and CR5 never turned on at the same time. That's safety, because we do not want to run the up motor, the down motor, and the up motor at the same time. You never want to run both motors at the same time. So that's what the CR4s and CR5s are. They are complementary. If CR5 is turned on, CR4 will be open. If CR4 is open, CR5 will be turned on. So that's the ladder diagram about this. The author will simplify this. So that's the simplified version of the ladder diagram. It is identical to the previous one. What's the difference? The difference is it will remove CR1, CR4, and CR5. Remove 3 latches. Not remove 3 latches. Actually, just remove 1 latch. This is a remove CR1, CR4, and CR5, but added M1 and M2. M1 and M2 are also latches. Control the motor. So this is just the simplified version of the previous ladder diagram. We have a class. Everybody take 272 already? 372, I'm sorry. PLC design. So in PLC design, you have all semester to study this subject. But today we just have 1 hour. We go through pretty quickly. I have a problem with the author's design. I think it's potentially can be unsafe. Why I have a problem with author's design is this. Notice the start button and the down button are identical buttons. That's the stop button. So when you push the stop button, everything stops. When you push the start button or down button, they are identical. That is extremely confusing. As an operator, when I push start, I just want to turn the power on. I do not want the motor to move down because now it's the identical function. Actually, pushing start and pushing down is the same thing. Why you have 2 buttons, which is basically the same? This is I consider potentially, if not a good design, potentially can be dangerous. If not dangerous, it's not that good. So what I'm doing here is that's my design. My design is in the blue. Here is the star latch. So when I push start button, I will not turn on any motor. All I did when I push start is energize CR3. Turn the power on. CR3 is the power. So CR3 will turn on. So I will provide the power. I may put even 1 here, but not necessarily here. Anyway, so the first run, I have 1, 2, 3, 4 runs. And it's also a clear design than the authors because it's so easy to understand. The first run is the start logic. Whenever I push start button, I will turn the power on. When I will push the stop button, I will turn the power off. You see here? CR2, when I push CR2, it will disengage. And basically de-energize CR3 and turn the power off. So start, stop. When I push stop, it will open this and stop everything. Stop everything. Start, stop. And then I have a down and up run. I push the down button, it will engage M2. I push the up button, it will engage M1, which is up motor. And also M2 and M1 are complementary. So when M2 is running, this will open. That means when I'm moving down, if I push the up button, the motor will never turn on. The up motor will not, because this is disengaged when the motor 2 is turned on. This normally open, close will be opened. So when M2 is energized, this will open. When this is open, this part doesn't work. You can push button 100 times, nothing happens. So does when M1 is energized, this will open. When that open, this part will not turn on. So that's the safety. So I will prefer my design over the author's design right here. the author design, I think this is potentially a problem and a surprise to the operator. You push start button, all of a sudden the platform moves down. You think you make a mistake. So anyway, that's two design. One is the 4 buttons on 4 runs. One is the author's, the 2 buttons on the same run. I never understand this logic, why we have 2 buttons identical on the same run. Anyway, that's the ladder. So that's our second topic. So the first topic is what it is. Second topic is how we do it in the old days by using relays and with a ladder diagram. The third topic is how we do it today. Today, PLC completely replaces all these relays. Why? Because relay is hardwired. Every time, for example, if you change a car model, a team works in automobile manufacturing, works in GM. So in their manufacturing plant, they have new car models every year. So when they have a new car model, in the old days, the engineers have to rewire all those relays because they have to redesign the ladder diagram. With a redesigned ladder diagram, they have to actually physically rewire the ladders, the relays. That is extremely time-consuming and can have human errors. So instead of having engineers or technicians rewire or re-hardwire all the relays, how about use a computer to simulate those relays? So that's what the PLC came to play. PLC is just a specially designed computer. Instead of rewire the relays, we just reprogram the computer. And that is much easier. So PLC will simulate all the relays, relay actions, the delays, and no need to rewire the relays. So that's quite an advantage. So PLC came from this assembly line replacing all the relays. So let's look at the PLC. Not only we have a limit relay, also PLC can have unlimited relay. In theory, it's limited, but it's almost unlimited. For example, if an assembly line needs 20 relays, you have to physically buy 20 relays. But a PLC, by using software simulate relays, we can just add code, add 2 relay modules, relay software. So we can have 100 relay, we can have 200 relay, just one PLC. You need 200 relay, you just put a new code. And also each relay can have unlimited contacts. That's this, unlimited number of contacts. That's relay number 1, right? Relay number 1 physically has limited number of contacts. Some have 4, some have 1, some have 2, some have 3, for example. But when we use in PLC to simulate relays, it's just computer memory. As long as you have enough computer memory, the number of contacts are unlimited. So that's the advantages of a PLC. So this is a typical PLC. In the center is a computer, and then you have inputs and outputs. Input and output, and computer. Then most importantly is the programming software. This programming software because the control engineers is not again, like I said, they are not computer engineers. They do not want to write a C code or assembly code or Java or whatever code. They don't like programming. So basically they use the ladder diagram. So that is the programming. So this is called the so the programming is done graphically. So the programming environment is a graphical programming environment, almost identical to their ladder diagram. So those control engineers are very familiar with the ladder diagrams, so they can easily use that graphic programming tool. Or this will be a graphic programming tool, like here. This is one of the graphic programming stations. So the control engineers just push buttons here and do a graphic programming. That's the ladder diagram right here. Once the control engineer finish programming the ladder diagrams, it will hook up to the PLC and download the program to the PLC. Once the program is downloaded to the PLC, you are done. So this will be downloaded, and then you can start testing. So that's quite an advantage compared with before. It may take you weeks or days to rewire those relays. Now with the PLC, you can just reprogram and download it in a matter of minutes or hours, 1 or 2 hours. You can reprogram the whole PLC. On assembly line, you might have dozens of PLC, all need to be reprogrammed. So the control engineers will go to each PLC station and reprogram all the PLCs, and then the assembly line is ready for the new car model, or the new serials, or the new whatever product you want to create. So that's the PLC. Input CPU module, output module, and the programming station. The programming station can be a computer, a laptop, or a dedicated programming station like this. Again, that is for a matter of easy programming, because control engineers sometimes in the early days don't even like laptop. They are intimidated by the computer, so they prefer something like this, dedicated, just the graphic interface, do the coding. But today everybody use a computer, so no problem about that. So we can use a laptop computer to do the PLC programming. So you can have that's another example of a programming station. I prefer a laptop over this, but some people may prefer this over laptop. Anyway, that's just a personal taste, personal preference. Another last topic before we move to example is PLC is a computer. We have to remember the PLC is just another computer. It's a special computer. In a lot of cases, overpriced computer. Think about the computer we purchase. Costs a couple $100. We have the cutting edge technology. And how about PLCs? The PLC is the computer inside generally is 20 years old, 30 years old. So if you are in the computer industry, you know a computer 30 years old worth nothing, right? But unfortunately, those PLCs sells for thousands of dollars. So it's an old computer, obsolete computer. It's a special computer. It's an overpriced computer. Put it this way. So anyway, it's a computer. If it's a computer, it's a sequential machine. That means the computer will do 3 phases. Computer will read the inputs. Computer will execute the code, the logic. Computer will send the outputs. In, execute, out. In, execute, out. Basically, computer will first read the inputs. Those are the sensors, the buttons. And then computer will do some logic calculation. And then computer will send to the output modules. So it takes time, start to finish. Today's computers are super fast. Today's computer, start to finish, we are talking about nanoseconds. Today's computer. But unfortunately, PLCs, like I said, are overpriced, extremely old computers. Those computers your grandfather used to use. So instead of nanoseconds, they are a million times slower. Milliseconds. Milliseconds means 1 million times slower. Think about it. You pay thousands of dollars to buy a extremely slow computer. That's what it is. Of course, the newer models are faster, but it's still 10 years, 20 years behind. So we are talking about the milliseconds, milliseconds here. They are called execution or scan time. So you have to be aware of the scan times of your PLCs. That means you cannot expect PLCs to do something faster than it physically possible. It's a sequential, slow computer. It's handling instructions in seconds, in milliseconds, like my computer over here. This computer, again, doing the same thing. It will execute 3,000 instructions every second. So this computer also, we are talking about milliseconds. Actually, people build a PLC based on this computer. And they sell for $200 or 100 something. So you can buy a simpler PLC based on this computer. This is also a slow computer for about, but almost all the commercial ones cost you thousands of dollars. But this is just a small hobby PLC. So you can buy a PLC, small hobby PLC, to control whatever you want to control. For example, if you have a smoker, if you have some automation around your house, you can buy one of those hobby PLCs, which are much. Some of them cost only $50, which is already overpriced. To be honest, $50 is already overpriced. If you charge 5,000, it's.
I have a question.
Yes.
What program do you use for that? For the basic stamp to program that?
It's a ladder logic. If it's built as a PLC, you download a ladder logic compiler.
Which one do you use specifically?
It's programmed same way as all the other PLC are programmed. They call PLC because the way, so PLC, you only call this PLC because you program all the PLCs identically. So all the PLC are programmed almost similarly. Ladder logic, graphic way. You program it using graphics instead of writing code.
Right. Yeah. I meant which like what's it called? In our PLC class from last semester, we used, I think, what it was, RSL Logics or RS Logics or something like that.
Yeah, that's a $1,000 control PLC. Yes.
Okay.
Yeah, that's an industrial PLC. We use that because our graduates, that's a very good career opportunity. The PLC engineers, program engineers, are on high demand. And many of our graduates actually became PLC specialists. I have one of our graduates. He works at Black & Veatch. He right now is the PLC expert, the expert of PLC at Black & Veatch in their department. Everybody has a question or has a PLC related issue, goes to him. He is a PLC expert. He handles all the PLC programming for that department. And he came back to me and he said he's a PLC expert. I said, how are you doing in the PLC class? He says he's not doing very well. He hopes he pay more attention when he studied PLCs during college. Because at college, he's a smart kid, but he didn't pay attention. He didn't think that can be his future career. So PLC is a good career opportunity. I personally do not have a lot of experience on PLCs. Although my specialty is computer, I rather program the computer directly instead of using this graphic tool to program it. That's just another way to program the same computer. Of course, this is obviously much easier for the control engineers who are familiar with this ladder logic. All right, looks like some of you already took PLC class. In that case, you might know more about PLC than I, because I never took a PLC class. And I never teach a PLC class. So the last part of today's material will be the programming of PLCs. Programming of PLC. And you have your input module, PLC input modules. You have your power module. And you have your CPU module. That's your CPU module. And then you have your output module. That's your output module. And every module, input module has addresses. That's how computers do identify inputs and outputs. And so all the input has an address. So in this case, it's 0, 1, 0, 2. All the outputs also have address. In this case, start with 8, 9, 10, 11. So it keeps going on. So that's the output address. That's your input address. And with that, you will translate your ladder logic into a PLC diagram. That's a physical ladder into a programmed ladder diagram. So there is a little difference between the ladder diagram you use to control your PLC and the ladder diagram you draw for the relay logic. So this is a ladder diagram you draw in the old days. In the old days, this is relays, 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 relays. And the contacts, contacts, sensors, 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 and sensors. And now you need to move from here, the upper half page. When you program a PLC, PLC doesn't care this. So what you need, when you program a PLC, you need to move from here, the upper half, to the bottom half. So this is the bottom half. Instead of a start button, you see here, start button, When you program PLC, it's just a contact. And then you will tell PLC 01, that's address, is a start switch. So that's the input labels. You also have to tell the pin. So that is actually for humans. Without this, humans cannot understand this diagram. But for computer doesn't care. All computer need is this address. So 01, 02, relay number 16, number 8, number 9. That's the output relays. So we have output relays 1, 2, 3, 4, 5. How about the sensors? Let's look at the sensor. We have sensor right here. That's simply called 32, input 32. Sensor, input 32. Sensor, temperature sensor, right here, temperature sensor. Input 04. So actually, to program a PLC, we actually use a simplified ladder diagram. By simplify, I mean go from here to here. All the sensors, all the push buttons, all the contacts are all replaced just by inputs. So those are the inputs. They are normally open inputs and normally closed inputs. So there's just two inputs, normally open, normally closed. And then we have timers. This will be a timer. Timer. This will be relays. So computer can have unlimited timer, unlimited relays, unlimited contacts, unlimited contact. All right. So once you've done this is the graphics. So on your station, just enter the graphics right here. So the control engineer will just enter the graphic on every run on this ladder diagram, and then download to the PLC. Then his job is done. And the PLC engineers, their starting salary is at least high six figures. One of my graduates, when he was looking for jobs, he actually showed me a job search. When the job title is PLC, has something related to PLC, salary is actually upper six figures, not the lower six figures most of our graduates get. So, but you have to have some kind of credibility, some kind of proven track records of. So it's not. It doesn't mean you will get that job right after college, but after a couple of years of working, getting more experience, that is where you can get a very stable, relatively high-paid career, PLC. All right, that is all I have for today. On the lab part this week, I do not have a lab PLC demo. I don't have a PLC around the house. So instead, and also I'm not, like I said, I'm not a PLC expert. So instead of having a demo, I will give you guys a YouTube video. So this week's lab demo is a YouTube video. So let me put the link on chat. Let me grab that link. I will also post it on Canvas. So this Wednesday, if you have questions, I will also be here answer your questions. But other than that, we will not have a regular lab session. Instead, please purchase all the material required for the PID project, and also watch this video. Let me post the.
Hi, I'm Dr. Amy Kill.
This is the link.
And I've been using Doodly now for a few weeks to create these really fun.
So that's the YouTube link for the PLC demo. PLC demo. There are many PLC demos, but this one I found is a very good introduction. It has a real-world project. It started with the physical, ended with the physical world. That's what I like. I do not want something started abstract, ended abstract. That is not a good demo. So this is a PLC demo. It has two parts, so watch both parts, part 1 and part 2. This will be this week's lab. Also, order the parts. The parts I have on Canvas. I posted on Canvas also. All the parts. Very few parts. Most important part is the PID controller. Anybody have questions? Have comments before we end this session? Anybody already got the PID controller? I know some of you already had it.
Yeah. Mine should be arriving next week, I believe, Thursday or Friday. Hopefully.
Oh, next week? Perfect.
Dude, you better not get yours before me. I'll be pissed.
Tim ordered last month, still haven't got it.
No, I contacted them. They just said they shipped it and it should be here the last week of October, no later than the first week in November.
Oh, okay. Oh, they already shipped it from China?
Yeah, from China.
Oh, really? Wow.
Yeah.
I hope the ship. Okay.
Yeah, I hope it gets here next week.
Yeah.
Not in November. I have all the other stuff.
Perfect. Anybody else?
Yeah, so I just needed the controller, the lamp, and the power source, right?
Mm-hmm.
As well as some wires.
Yeah,
which
some
I've got.
wires, some tools. Yeah, some screwdrivers. Yeah.
I got those things, yeah.
Perfect.
Boxes too.
So I tried to hook up the lamp right to the controller. Is that how I'm supposed to do it?
Yes. Don't do it right now. Yeah. Actually, through the controller. Yes, through the relay. The lamp is through the relay. The lamp is turned on and off by the relay.
The relay.
Yes, the lamp is on and off through a relay. And then the...
Well, hang on. So is the relay in the controller itself, or is that...
Inside, yes, inside the controller.
Okay, yeah.
So that's how you control the power to the lamp is through the relay. Anybody else? B, did you got your controller?
Yeah, I got everything.
You got everything? Perfect.
Yeah.
You're way ahead of everybody, half of the class.
Yeah, I ordered all of them at once.
You already arrived?
Yeah.
Wow. Where did you order? Where did the team order? He's like travel around the world.
Great value one. That's why it's taking longer.
What?
Said you got the cheap one. That's why it's taking longer.
No, probably because I bought the more expensive one.
But mine is like 75.
I don't know. I ordered mine last week off Amazon.
Yeah, that's where I order mine too.
Looks like Tim's computer maybe VNC'd to China. So people thinking you are from China.
What? Yeah, I ordered it on October 14th, so just 5 days ago.
Okay. All right, with everybody ordered the parts and on the way, we're looking at getting started next week for PID incubator. So you can have a couple of chicks in your backyard next in the winter. All right. Anything else before we? I will see you guys next week.
See ya.